In exercise 2132, we're trying to turn one functional group into a different one. We're going to do this over and over again. So we see on the left here an ester. We have a carbon double bonded to oxygen, single bonded to an ether. And so we want to view that ether, that methoxy group there, sort of as our leaving group. And that's going to be replaced ultimately by chlorine. And so that we end up with an acid chloride. Now you can think about this going forwards or going backwards. One thing you definitely want to know is that there's only one way to make an acid chloride. You have to make it from a carboxylic acid and you have to use thionyl chloride, that really toxic compound. And it's really important to know because this is a really reactive carboxylic acid derivative, so it's sort of a gateway to a whole bunch of reactions, and there's only one way to make it. So you definitely want to know that reaction. Now that's if you're thinking backwards, if you're doing retrosynthesis. Starting with the product and thinking how can you make that, and working your way backwards, trying to connect that to your reagent. If you think forwards, well, okay, if we know we have to make this carboxylic acid, how can we make that from this ester? And we've drawn the mechanism for this many, many times. This is the acid-catalyzed hydrolysis of an ester. All you have to do is add some H3O+, and the H3O+ will, with an acid-catalyzed mechanism, break open. It'll first add a proton to the carbonyl oxygen, turn this carbonyl carbon into a better electrophile. The water that's left after you transfer the H+ will act as a nucleophile and ultimately will turn into the OH here. So you'd end up with this carboxylic acid, and somewhere else floating in the solution you'd have methanol. But we're not interested in the story of that carbon molecule. We're interested in the story of this backbone. So that's it. There's really only two steps for this. You do acid-catalyzed hydrolysis of an ester to get a carboxylic acid, and once you have that carboxylic acid, you can treat it with thionyl chloride to get the acid halide, the acid chloride there. The mechanism for this reaction is a little strange, so I don't think we've done that before, and I would like to do that now. It's not a mechanism that you need to have memorized. So I'm just adding this here for extra knowledge for people who are interested. So if you're not interested, that's okay. I understand that there's only so much time in your day. So if you just want to memorize this, that's okay. I mean, it kind of breaks my heart, but it's okay. You can scrub to the next place where you see B. For right now, I'm going to explain how this happens, because we've seen thionyl chloride somewhere else. We've seen it in making nitriles. If you treat an amide with thionyl chloride, it turns it into a nitrile. So I want to make sure that when it's introduced here, making a change that may not immediately seem clear, that it's explained. So ultimately, the SOCl2 is a sulfur double bonded to oxygen with a chlorine on each side. And that's the thionyl chloride. And you'll see that this really resembles a carbonyl, right? It almost resembles an acid chloride. You just have a sulfur where you would otherwise have a carbon. So if you have your carboxylic acid here, the first thing that happens is very similar to the mechanism that we saw for making nitriles out of thionyl chloride. These lone pairs are allylic to this pi bond. And so they're constantly, the actual molecules in average of the two resonance structures, they're donating electron density toward that direction, which makes the pi bond especially nucleophilic. And you can use that to attack the sulfur, and the pi bond breaks here. So if you're sort of classifying that, that would be a nucleophilic attack. And we sort of get a tetrahedral intermediate after that. So we sort of get a tetrahedral intermediate out of that. We have this oxygen now double bonded. Oops. Here now has a full positive charge. This oxygen is single bonded here, and it's now bonded to a sulfur with just a single bond to this oxygen. and 2 chlorines. So that's sort of like a tetrahedral intermediate. And that tetrahedral, the oxygen there is very unstable, and so just like in the tetrahedral intermediates of nucleophilic acyl substitutions, it snaps back down and kicks this awesome chlorine leaving group off. So that is ultimately loss of a leaving group. The second step in a nucleophilic acyl substitution. So, oops, you have a methyl group there. So, what we have at this point is this molecule. That molecule there, and, oops, this should be a hydrogen, and very similar to the mechanism for how you make a nitrile out of these. A sort of base can come along, here the chloride is the base, and steal this hydrogen. The electrons go here to stabilize that positive charge, so that's a proton transfer. Now, let's step back and think about what we accomplished so far. We did a nucleophilic acyl substitution to turn the OH into this big, fat thing. But what you'll notice about this is that that is actually a really, really good leaving group. It's a very good leaving group because if it left, the oxygen here could handle having a negative charge. That negative charge would be allylic to this pi bond, and so it would be spread out over those 3 atoms, plus the electronegativity of the chlorine would help to spread it out over 1 more atom. So that molecule can really handle having a negative charge, and it's a really good leaving group. So that's what we accomplished so far. And now, with that leaving group, you can sort of think of this like another carboxylic acid derivative. You have the carbon double bonded to oxygen with a leaving group attached to one side, but now the leaving group is just amazing. So that's what we accomplished in this first step. The chlorine that left can come in and act as a nucleophile and burst open this pi bond. So we're sort of doing another nucleophilic acyl substitution. And this is nucleophilic attack in that. So what you end up with after that step is just 1 bond to this oxygen, which now has a full negative charge. You have a chlorine here, that's the chlorine in what will ultimately be the acid halide. And you have your tetrahedral intermediate with a really unstable oxygen. And as we've seen, this will snap back down, but now we have a leaving group that's even better than a chlorine, if you can believe that there is such a thing. And so this pops off the molecule. And what we're left with is, a double bond to this oxygen. The chlorine is still there, and we have a sort of strange sulfur compound with an oxygen on one side. Now, ultimately, that sulfur compound is going to degrade. So this last step, you could sort of think of that as loss of a leaving group. So this is ultimately, the sulfur compound is ultimately going to degrade, just like we saw in the formation of nitriles. That negative oxygen forms another pi bond and kicks the chlorine off, so that you have sulfur dioxide and a negative chlorine. Right, this is going to be sulfur dioxide. But the important thing that for us in organic chemistry, the story of the carbon molecule is that it becomes an acid chloride. So that we started here with a carboxylic acid, and we turned it into an acid chloride. Conceptually, overall, what we did is we saw that you can't just treat this with sodium chloride, because even if chlorine comes in and acts as a nucleophile to give you a tetrahedral intermediate, even if, let's say you had something like this, even if you had a chlorine come in as a nucleophile, and chlorine is a strong nucleophile, so that's not the issue. It's very polarizable, so it can come in and act as a strong nucleophile. The problem is, once you have the tetrahedral intermediate, and this negative oxygen here on top comes crashing back down, it kicks off the best leaving group, which is the chlorine. And so the struggle was to, and that just gives you your carboxylic acid back, the struggle is to have a better leaving group than chlorine on the tetrahedral intermediate. And that's the role that thionyl chloride plays. You attach the thionyl chloride to the oxygen, and it turns into a better leaving group even than chlorine, so that the chloride can come in and attack, and when this negative oxygen slaps back down, it kicks off the better leaving group rather than the chlorine, and leaves you with the acid halide. So that's why there's only one way to make acid halides, and it involves using thionyl chloride. So anytime you go from a carboxylic acid to an acid halide or an acid chloride, you would want to use thionyl chloride, SOCl2. Okay, we're going to use that a bunch because the acid chlorides are really useful. They're the most reactive, and so of the carboxylic acid derivatives, and so they really increase your efficiency, the efficiency of your reactions. So if we look at these here, you'll notice you have a carboxylic acid. You should think of the OH as a leaving group. We see that a different group comes in. We can sort of think of that as a nucleophile. That's one difference. So we're going to have a sort of substitution reaction happen. And then another difference is we have 2 bonds to an oxygen. Those are replaced by 2 bonds to hydrogen, to 2 implied hydrogens there. So that's a reduction. So we're going to have to do a substitution, the green and red, and a reduction, the purple. Well, we want to do the substitution first, because so long as we have this double bond to the oxygen, we can use it to make this awesome electrophile. We can use it to do a nucleophilic acyl substitution. The problem is that ammonia is not the best nucleophile. It's an okay nucleophile, but it's not the best, and, I mean, it doesn't have a full negative charge or anything, and the carbonyl carbon in the carboxylic acid is not the best electrophile because the lone pair on the oxygen is able to donate some electron density through resonance to this carbon, so the charge on it is small. So we can't acid-catalyze it either, because ammonia is a base, and it will sooner accept the H plus to become NH4 plus than this would. So we cannot do a nucleophilic acyl substitution by treating the carboxylic acid with ammonia. What we can do is change what derivative this is. We can turn it into something that is more reactive. And that is an acid chloride. So if we take this, and we just drew the mechanism for this, if you take the carboxylic acid and treat it with thionyl chloride, it replaces the OH with a Cl. So now we have the acid chloride. Now once you have the acid chloride, this is an amazing electrophile. It will react even with a weak or moderate nucleophile like ammonia. And keep in mind you'd want to use excess ammonia because you're going to do a proton transfer to take one of the H's off there. So that will do a nucleophilic acyl substitution. You'll replace the chlorine with the nitrogen. Notice that there's only 2 of the 3 hydrogens because the extra ammonia took off one of the hydrogens in a proton transfer reaction to stabilize the charge. Okay, so that accomplished the substitution. So if we're sort of writing out a schematic, the first step, thionyl chloride, and the second step, excess ammonia, those accomplished the substitution reaction that we needed. So the second step is what's in purple here. Oops, I should say substitution. Okay, the second step is what's in purple, and that's reduction. We have 2 bonds to oxygen, an electronegative element, getting replaced by 2 bonds to hydrogen. So we want to use a hydrogen nucleophile. And here we're reducing it as much as possible, so we might as well use a strong hydrogen nucleophile, and that would be lithium aluminum hydride. Now remember, that, that replaces the bonds to oxygen with bonds to hydrogen. You still have to fill in hydrogens on, you still have to follow up and make sure that everything is protonated, and so always after using lithium aluminum hydride, you do a water wash. So after you do the substitution, you're going to want to do the reduction. That's the purple thing. And that's going to be first with lithium aluminum hydride, and follow that up just to stabilize everything with proton transfers with a water wash. So overall, the solution to this is going to be this whole process. 4 steps. You treat the carboxylic acid with thionyl chloride to turn it into a more reactive acid chloride. Then you can treat it with excess ammonia to turn it into an amide. Last, you reduce the carbonyl on the amide with lithium aluminum hydride, and you stable stuff by doing proton transfers from water. And that leaves you with your amine. Okay. For C, now here we have an anhydride. You'd want to see the anhydride and notice that what you have is a carboxylic acid derivative. You have carbon double bonded oxygen bonded to a leaving group, and so that's a key conceptual thing here. Acid anhydrides often look scary and confusing, but you just want to look at that oxygen single bonded to a carbonyl as a leaving group. So how do we replace that leaving group with what we have on the other side, a chlorine? And you could do this either forwards or backwards, but when you see an acid chloride as your product, instantly you should think there's only one way to make that. I have to have a carboxylic acid, and I have to use thionyl chloride, SOCl2, just like we saw in the mechanism above. It's the only way to make an acid chloride. So we know we'd have to get this somehow, but how do you get that from this molecule? All you're doing is replacing the leaving group here with an OH. And that's easy enough. You can just do that with water. Remember, this is really reactive. The most reactive molecule is an acid chloride. The most reactive, not molecule in general, but the most reactive carboxylic acid derivative is an acid chloride, and the second most reactive one is an acid anhydride. And you don't see those molecules as much in living things because they're so reactive. They don't last very long, so they're not useful for creating structures that are meant to persist over time. So, because it's so reactive, we don't have to acid catalyze it. It'll just react with water. You can do this. Water is a good enough nucleophile. This is a good enough leaving group to make that transformation happen. So this process only has 2 steps. The first step is shake it up with some water. And the second step, carefully shake it up with some thionyl chloride. All right. This next one. So when we look at this, we see 2 things. We see a carboxylic acid derivative to start, carbon double bonded to oxygen, single bonded to an ether, and so we have an ester, and you'd want to see that ether group as the leaving group. And we see another group coming in, this NH2, and so that could be a sort of substitution reaction. That's one thing that's happening. The second thing that's happening is we have 2 bonds to oxygen here that are replaced by 2 bonds to implied hydrogens. And so that is going to be reduction. So we'll have 2 parts. We'll have substitution that we have to accomplish. That's the green and red. And we'll have reduction that we need to accomplish. That's the purple. Okay, well, how do we do this? Well, we know we can do a lot of stuff with esters. Maybe the one we've done most often is the acid-catalyzed hydrolysis of esters. We drew the mechanism for that many, many times. That's how triglycerides break apart. So we could do that. I mean, well, maybe let's just make that note down. Just brainstorming. Could be completely wrong. Maybe we'll erase it, but I definitely think of that when I see an ester. You can acid-catalyze. You can do acid-catalyzed hydrolysis, and that will turn that into, in our case, we're interested in the carboxylic acid, but we'd also have an alcohol in the solution. But we want to follow the story of this carbon skeleton, so we'll let the alcohol go its way, and we'll focus on the carboxylic acid. Maybe that'll be useful, maybe it won't, who knows, it's an idea. Well, I'm stuck there, although, I mean, I guess we can try to replace that with an amine somehow, although we can't do that at once. We've seen that in the previous example up here. Because, first of all, this is an acid, and if we try to treat it with excess ammonia, ammonia is a base, so you'll end up doing an acid-base reaction. You'll get the carboxylate, the negative charge on that oxygen there, and then this would turn into NH4+. So you do an acid-base reaction, and you wouldn't get the transformation you want. So if we did want to add a hydrogen there, we'd have to change this leaving group. Well, if we're going to change it, we might as well make it more reactive. And carboxylic acids are uniquely positioned to make the most reactive of the derivatives in acid chloride. Okay, well, we still have some problems, but we can see that this chlorine can be replaced by this ammonia. All we have to do is treat it with excess ammonia. The first equivalent will replace the chlorine, and the second equivalent will steal the third hydrogen. It'll act as a base to stabilize the first equivalent by stealing the third hydrogen after it adds on. Okay, well, we're definitely closer. We've accomplished the substitution. How about the the reduction? Well, we start with 2 bonds to oxygen. We get rid of both of them, so we might as well use as strong of a reducing agent as we can. The strongest reducing agent we know is lithium aluminum hydride, and then you just follow that up with water to make sure everything is protonated and all the charges are stabilized. So, overall, you would treat the ester with an acid, so you could do acid-catalyzed hydrolysis. That gives you a carboxylic acid. You can use the carboxylic acid to make the most reactive and efficient carboxylic acid derivative, an acid halide, with thionyl chloride. Once you have thionyl chloride, you can finally accomplish the substitution, get the amide, by adding excess ammonia. Now that you have the amide, you just have to do the reduction. You can use a strong reducing agent like lithium aluminum hydride, and then just to make sure everything's stabilized, you do proton transfers with water. And so those 5 steps would be the 5 steps you'd need to take to make this transformation happen. Okay, E. With E, we have a carboxylic acid to start, and we have a derivative to wind up. Now we've only learned a couple ways to make these cyanides. One of them is to have a cyanide come in as a nucleophile, but we can't do that because the carbon is already there. We don't want to add another carbon. So instead, we have to transform this functional group into this other one. The way that we learned how to make a nitrile, and we drew the mechanism for this in the video on the reactions of nitriles, was to treat an acid, was to treat the, we can make the nitrile by treating an amide with thionyl chloride. So in other words, if we had the amide here, we can get rid of this oxygen, make it a good leaving group by adding thionyl chloride. And that will take the electrons there, those extra 2 electrons, and it'll bond it to the nitrogen, so ultimately it turns into that carbon triple bonded to nitrogen of the nitrile. That's what that CN is. So the way you can make a nitrile is by treating an amide with thionyl chloride, and we walked through the mechanism for that in a previous video. But you can see it's doing a similar thing as the mechanism we drew just a second ago with thionyl chloride. It's turning the oxygen into a good leaving group. You can see it disappears, or leaves the molecule. So how can we turn a carboxylic acid into an amide? Well, we know we cannot just treat it with excess ammonia. That's just going to do the acid-base reaction, as we saw in the previous exercise, this one above here. So instead, we can turn this into a different derivative, the most reactive one, an acid chloride. And this is really nice because it illustrates the different roles that thionyl chloride can play. Two really important reactions. You can use thionyl chloride to change a carboxylic acid into an acid chloride. Really crucial because acid chlorides are very reactive molecules, so they're really useful. You can get a lot of things done with them. The other way we can use thionyl chloride is we can take an amide and use it to turn it into a nitrile. So now we just have to connect the acid chloride with the amide, and we can easily make that transformation happen. It's a nucleophilic acyl substitution. The chlorine is the leaving group, the amine is the nucleophile, so we could just have NH3. The first equivalent of NH3 is the nitrogen that adds. You'll notice a hydrogen is missing. You did a proton transfer to the second equivalent of the NH3. So overall, your recipe here is thionyl chloride, followed by excess ammonia, followed by another step of thionyl chloride, doing a very different reaction, like you're making a different reactant into a different product, but through a similar mechanism, by turning the oxygen into a good nucleophile. A good leaving group. So that's E. F is really straightforward. You'd want to look at this and see this leaving group. It's very reactive, so how can you make that happen? Just treat it with water. Really just shake that up with water. Water is a good enough nucleophile to attack the carbonyl carbon. You get the tetrahedral intermediate. It snaps back down. This leaves, and you just do a proton transfer to turn H2O into OH. So that's it. One step, water, you're done. And that nucleophilic acyl substitution. For this one, you have an acid chloride. It's a carboxylic acid derivative. You'd recognize the chlorine as a leaving group, and we want it to be replaced by a nucleophile. The nucleophile we can use here would be ethanol, so ETOH. Now, we don't have to make this acid-catalyzed, because this is already really reactive. You would make it acid-catalyzed if you had a carbonyl carbon that was not as reactive, like an ester, or in a carboxylic acid, or in an amide. But because an acid chloride is already so reactive, we don't have to add that here. We just need a base to take the hydrogen off, and the base that's most often used is a base called pyridine. Sometimes you might see that just abbreviated as PYR. It's like benzene if one of the carbons were replaced with a nitrogen. So you have sort of benzene, but with a nitrogen there. The lone pair on top is not involved in the resonance, or in the aromaticity. The py orbital is already taken there, right? If you have the py orbitals for all the pi bonds, you can see the py orbital is already taken for this pi bond, so this lone pair can't exist in it, and can't be conjugated with all those other pi bonds. So instead it's in an sp2 orbital just pointing out into space, and so it can act as a base. Ultimately, it steals the hydrogen here, which you don't see in your product. It steals that after it adds after it does the nucleophilic acyl substitution. And you actually know pyridine, because you've seen it act as a base before. After it takes an H+, it's called a pyridinium. And pyridinium is the P in PCC, which stands for pyridinium chlorochromate. It's the positive charge on pyridinium that stabilizes the chlorochromate and makes it a weaker oxidizing agent. So that's all you'd have to add here. Ethanol and pyridine. And you can make this transformation happen from an acid chloride to an ester. H is interesting. With H, you might at first look at it and you'd say, okay, I have an amide, carbon double bonded to oxygen, single bonded to an amine. The nitrogen is going to be my leaving group, but what is my nucleophile? And you'd see this hydrogen. And you may be tempted to say, okay, hydrogen nucleophile, maybe lithium aluminum hydride. Now, there are a couple problems with that. The first problem is this is a strong reducing agent. This will not just stop at the aldehyde. Another hydrogen will come in and reduce this down to an alcohol. Another hydrogen nucleophile will attack this aldehyde carbonyl carbon and reduce this down, add another hydrogen there, reduce it down to an alcohol. I mean, ultimately it would have a negative charge, but then it would steal a hydrogen from water. So you get that. Well, that's not what we want. And so we can't use lithium aluminum hydride to make that. What we can use is a weaker reducing agent. If you remember, a lithium aluminum hydride is such a strong reducing agent because aluminum has very low electronegativity. And so all of those hydrogens have a lot of electron density on them. But you can make it a weaker hydrogen nucleophile by adding electronegative elements nearby. Now oxygen needs 2 bonds, so you can have it bonded to another R group, but those electronegative elements act over multiple bonds to pull electrons to themselves. That reduces the amount of electron density on the hydrogen, which becomes very small, and so that's a weaker hydrogen nucleophile, and it will only add once and only give you, and it will stop at the aldehyde. In other words, it will react with carboxylic acid derivatives, but not with an aldehyde. So we will have to do a reduction. We will have to use a hydrogen nucleophile, but it will not be lithium aluminum hydride. It will be lithium aluminum trialkoxy hydride. And that trialkoxy group is just using induction to make the hydrogen a weaker nucleophile. Okay, so we know we're going to have to use that eventually. But we can't use that, it wouldn't be the most efficient thing to use that on the amine. Because this is not very reactive. And also, the hydrogen could react with, for example, the nitrogen instead. Or it could react somewhere else in the molecule. But to improve efficiency, we want to turn this into an acid chloride. So the first step to doing that is doing acid-catalyzed hydrolysis of an amide. Just treat it with H3O+. We drew the mechanism for that a whole bunch of times. And so we can get this carboxylic acid from that. We'd also have ammonia in the solution. But we're interested in the story of this carbon molecule. Now, we still can't treat the lithium aluminum hydride with this because the hydrogen can attack a different place on this. It would be an inefficient reaction. This carbon is not the most electrophilic because the lone pairs here are allylic to the pi bond, and so stabilize the positive charge there through resonance. So we can turn that carboxylic acid into thionyl chloride, into an acid halide by adding thionyl chloride. And now we have the most reactive of the carboxylic acid derivatives, which is really efficient. And that's especially important because we're using such a weak hydrogen nucleophile. So it's important that we combine it with a strong electrophile. Otherwise, the reaction may not even happen. So then we can use our lithium aluminum trialkoxy hydride, and that would give us the aldehyde. It would only reduce it once. We'd replace the chlorine with a hydrogen only once. So overall, the recipe that you'd use is hydronium as one step, as a second step, thionyl chloride, and as a third step, lithium aluminum trialkoxy hydride. And then anytime you use any type of reducing agent, hydrogen or carbon nucleophile, you would want to follow it up with some water just to make sure that all of the charges are stabilized by doing proton transfers. So this is your recipe for that one. For I is, you have a nitrile here. This is a carbon triple bonded to nitrogen, and you're turning it into an alcohol. Now, the first thing we need to do is get rid of the nitrogen. And you can do that with a hydrolysis. Really, all you have to add is hydronium, and it turns it into a carboxylic acid. We've seen the mechanism for this in the video that we made on the reactions of nitriles. Ultimately, you do a proton transfer onto the nitrogen from this, and then water acts as a nucleophile to attack the carbon. That gives you one of your oxygens. And what you're left with is sort of an imine after that. And if you'll remember, imines get hydrolyzed in the presence of acids to carbonyls. And so that's kind of the way this works here. But in any event, you can view that mechanism in that previous video. We can do a hydrolysis to get a carboxylic acid, and you can see how much closer we are to our product now. The only difference here is the number of bonds to oxygen. Here we have 3, here we only have 1. So we want to reduce the number of oxygen bonds, and we can easily do that with a reduction. Here we're trying to reduce it as much as possible, so we use lithium aluminum hydride and follow that up with water to make sure that all the charges are stabilized. So overall, the whole recipe for this one would be hydronium, followed by lithium aluminum hydride, followed by a water wash. And that would allow you to turn that nitrile into an alcohol. So we've done, oh, and J, one more, okay. How about the opposite? What if you want to get the alcohol and turn it into nitrile? Literally the reverse of I. Well, we know we did a reduction at the end there. Here we're going to do an oxidation. And if you were just coming to this fresh, without having the hindsight of the previous exercise, you'd see 1 bond to an electronegative atom, and here you have 3. Forming the number of bonds to an electronegative atom is what determines oxidation or reduction. If you increase bonds to an electronegative atom, that's oxidation. If you reduce bonds to an electronegative atom, that's reduction. Here we want to increase them. We have just 1, we want 3. And so we want to do an oxidation. So the first step we can do here, the simplest oxidation we can do, is to just treat this with a strong oxidizing agent like sodium dichromate in water and sulfuric acid. And that will take that alcohol and turn it into a carboxylic acid. Now, once we have that, we need a nitrogen on this molecule. But we can't just add excess ammonia right now. When you see this, you see the OH, you think leaving group. We'd want to replace that with a nucleophile, like a nitrogen nucleophile, like ammonia. But we can't replace that, we can't attack this with a nitrogen because the nitrogen ammonia can act as a base. It would just steal the hydrogen there. So we have to change this into a less acidic but more reactive carboxylic acid derivative. And that would be using thionyl chloride to make it the most reactive carboxylic acid derivative, an acid chloride. Once we have that, we can treat it with excess ammonia, and this nucleophile will replace the leaving group. Now you'll notice there's 1 less hydrogen because you do a proton transfer to the second equivalent of the NH3. So now we have our nitrogen there. We're also just as oxidized. We have 3 bonds to electronegative elements here, 3 bonds to electronegative elements there. We just need the oxygen to leave, and as we've seen a couple times now, the way we can get that oxygen to become a good leaving group is to use thionyl chloride. So the thionyl chloride will turn an amide into a nitrile. So overall, our recipe in J is first to use a strong oxidation with sodium dichromate, Na2Cr2O7, mixed with water and sulfuric acid. That will turn this alcohol into a carboxylic acid. Once we have the carboxylic acid, we can use thionyl chloride to turn the carboxylic acid into an acid chloride. Once we have that, we can get the nitrogen on the molecule. We can use our weak to moderate nucleophile, ammonia, and that will react with this amazing electrophile without doing any side reactions. So we add that. Finally, we have our amide, and we just need to get rid of the oxygen. We turn it into a good leaving group with thionyl chloride. So the 4th step is thionyl chloride. So overall, Cl2. So overall, this is the recipe you'd want to follow to make that transformation happen. So in this video, we've seen a whole bunch of different ways to convert one carboxylic acid derivative functional group into another. And we'll continue our exploration of these types of reactions in the next